the junction chapter, and today we are going to talk about the p-n junctions. Okay. Well, if you have a p-type semiconductor and n-type semiconductor, let's say silicon, and then make a junction, then if that junction is in equilibrium, then the band structure is going to look like this. The Fermi energy level should be same everywhere, so that the conduction band and the valence band is going to be distorted like this, and then this is the p-type region, and this is the n-type region. Right? So we can distinguish three regions in this junction, where the far away to the left and right hand side is going to be neutral region, and at the center there is a depletion region, and there's some transition regions, let's say in between neutral and depletion there is a transition regions, okay? And in the neutral region, that's the far left and far right, the electron density in the n-type is going to be the donor density. We assume that every donor is fully ionized, okay? And that is not a bad assumption. And that is going to be expressed in this equation, okay? If everything is in equilibrium. And no net charge. In other words, N minus P minus ND plus NA should be the zero. So negative charge, electrons and acceptors is negative charge. Negatively charged particles, and hole and donor should be positively charged particles. So there's no net charge in the neutral regions, okay? And it means we are going to have a constant potential. Second derivative of the potential should be the zero, constant potential, and phi n is going to be expressed, we have discussed this before, okay, and then that is the location of the Fermi energy levels, and the p-type of potential is going to be expressed in this way. So there is a potential change from n-type and p-type according to these equations. Okay, so that the built-in potential in this junction and that is going to be phi p plus phi n, and that is Vt nd Na Ni square. So the doping level of a p-type and an n-type, you can create the built-in potential inside the junctions. So actually, this is a very amazing thing to notice. You have one single crystal of silicon, one piece of silicon, and then you add some foreign atoms, p-type on one side and n-type on the other side, and we can have some electric field inside. Okay, that's a very amazing thing to notice, and that is a very important thing, right? Now, on the depletion region, the potential is going to be, second derivative of potential should be related to the charges. Okay, that is a Poisson equation, as a matter of fact. Right? And we'll focus on this depletion regions. That is the most important part. And we're going to discuss about it in a minute. And let's just move to the transition region. We'll be back to depletion region in a minute. Okay. Region. The length of transition region. You have to use a computer to find this. And that is about 3LD, where LD is extrinsic device length. Which can be expressed as Vt thermal voltage, gamma, Nd minus Na. Okay, and then the number is typically about 300 angstrom. Not that big, okay? So, what we can see here is that when you make a junctions in the semiconductor, what's going to happen is that if this is a physical contact, okay, then if you draw the charge density, then we can distinguish three regions here where the far back and the far right, you don't have any charges. That's the neutral regions. And at the center, you are going to have some charges, negative charges and positive charges, something like this, okay? Charge means you don't have a free carriers. And we call that depletion regions. So let's say we're going to have some depletion regions where the charges, there is no free carriers. Why? Because the free carrier is an opposite charge. It has opposite charges so that it just annihilate each other at the center. How far? We don't know. And that is our main topic for the discussion in a minute. So this is the W, the total length of the depletion regions. And in this depletion region, there's no charges at all. And then you have to connect this somehow. And that is transition regions, which is going to draw something like this, okay? It has to be drawn something like this. So we can distinguish actually for three regions in terms of the charges. And this is a depletion, this is the region, transition region, and that is about typically 300 angstroms. Okay? And in our calculation, we assume the abrupt junction means this transition region can be neglected because it's anyway, it's about the 300 angstrom. So we can have this three regions. And the most important feature of this junction is the depletion region. What's going to happen in the depletion regions. In vacuum tube transistors is related to the vacuum states, okay? In the solid state vacuum, you should say. And the internal field is very helpful to characterize this electrical properties of these junctions, as you can see now. Now, we assume that step junction means they ignore transition regions. All right. So what we are saying here in this step junctions, we have a depletion regions, something like this, and this is the neutral on the left-hand side and right-hand side, and the length of this depletion region, total length is about it can be seen here, and in this depletion regions, there is only ionized donor and acceptor. No free carriers. See, when you dope the donors into 14 atoms into silicon, then if it is a donor, then it is ionized to give up one electron to the conduction band, something like this, so that every donor is going to be charged, positively charged, like this. And every acceptor should be negatively charged to give up one hole to the valence band, something like this. So every donors and acceptors in the semiconductor are charges. But in the neutral regions, this negatively charged acceptors, for example, it has one hole orbiting around this. It's not actually orbiting, but it is there. The number of acceptor should be equal to the number of holes in that substance. Okay, so let's just express this is connected to this acceptors, and the number is equivalent. It's the same number, so that it is neutral, right? And you can say the same thing for the donors, and one electron is corresponding to one donor. so that the total number, it maintains the neutrality. Okay, that's what happens in the semiconductors. But when you make a junction of this, these electrons and holes, they're free to move, so that they annihilate at the junctions, so that the some length, along the some distance, there is a region where this free carrier is null. There is no free carriers. And then only the ions is there, which is the donors and acceptors. So we have net charges here. And that charges coming from this donors and acceptors can be expressed by the Poisson's equations here. All right. Now, according to the Poisson's equations, the second derivative of potential should be related to the charges, and that is going to be the ND, donor concentrations. Okay? That's simply the Poisson's equations. And you can say same thing for the p-type region, where it can be said something like that. Let me minus xp and 0. Just follow the notations in the book. Okay, and the charge neutrality says NA xp should be equal to the ND xn. It means that the charge is here the xp, when you set 0, this is xn, okay? And the charge E here should be the same. Otherwise, it's going to have a net charge. And that's not going to happen. So, now electric field, which is a first derivative of potential, and you can get that by the integration of this charges with respect to the distance, and that is xn to x minus gamma nd dx, okay? And then that is simply gamma nd x minus xn. You can say the same. You can do the same thing for the p-type region, and then you can easily get this equation for the p-type region, the field for the p-type region. So, this equation just says that there is a potential for the n-type and p-type such a, this is xp and this is xn, and there is an electric field which can be seen something like this, okay? And then we can set the maximum electric field here. And that maximum electric field, just to simply calculate it from this equation. Where do I have that? You can, okay. This is minus gamma nd xn and that should be the same to gamma Na xp, right? And what about the potentials? If you do the integration with respect to x of this electric field, then you'll find the potential, and that is gamma nd xn square. Of course, you can do the same thing for p-type, and then the equation is it's going to look like this, and the built-in potential in this junction, most important thing to characterize the electrical properties of these junctions, and that is phi I is going to be phi p plus phi n. You just simply add those two things, and that can be expressed in terms of the maximum electric field, xp plus xn. Okay. Now the important thing is depletion width W can be calculated from this equations, and then that is going to look like this. So this is amazing. We can actually calculate, mathematically calculate the length of the depletion regions. If you do physically the doping, okay, and to make a junction, and the result, okay, on the electric field, built-in potential, and depletion width, all those kind of things can be calculated. And that is amazing. Okay. Let me just point out the one thing here before we go any further. In a vacuum tube, before 1949, the invention of the semiconductors, every transistor has been made by this vacuum tube. So in this vacuum tube, you physically make a tube in the vacuum, and you catch the filament, and then if you keep this filament inside the vacuum tube and then apply some voltages, then electrons is going to emit it, and we call this field emissions, right? And these electrons is going to be modulated by the grid. We call this grid. And in this grid, all you do is just to put plus and minus small voltages here. And then we set inside the vacuum tube the plate. We call this plate. Okay, and then receive the electrons which has passed through this grid. Okay, and this is related to the output. And the modulation we do in the grid to the grid is going to be called input. Okay, so depending on the input polarity of the volt potential, then the number of electrons which can pass through this grid is going to determine, and then this plate receives those electrons which has been passed through the grid. And so that's how it can work as a transistor, amplification and the switch and those things, right? Now, if you look into the junctions, this vacuum is related corresponding to the depletion region. In a solid state. Okay, this is a vacuum tube. And the field, electric field between the plate and the filament. Plate and the filament. It's not exactly what we are going to use the built-in potentials. And of course we are going to apply the voltages for this but basically we are going to use the built-in potential. And since the depletion region is less than 1 micron something somewhere, so that the field itself it can be reaches 10,000, more than 10,000 volts per centimeter, something like that. So this built-in electric field is not that trivial at all. Okay, so it is amazing. This is how we can make in a vacuum tube. The smallest one was the 2 millimeter size, the length, in 1949 RCA, the famous American company to make audios and videos and everything, at that time. And the smallest vacuum tube I know is about 2 millimeters in size. Now, if you use this solid state junctions, you can make a transistors micron size. So there's a tremendous difference, and the power of this transistor actually coming from the built-in potentials. That's what I try to emphasize. Okay. So with this knowledge, let's just think about the p-n junction capacitance, one of the electrical properties. P-n junction capacitance. You can see that the neutral regions in the P and N is separated by the depletion length, W. You can think the whole thing as a capacitor, right? So in a small signal case, we are going to think about the small signal capacitance, small signal capacitance. Small signal capacitance means we apply a low DC bias, and then for the measurements we superimpose the AC characteristic to get a charge difference. And this is the capacitance, okay? So small signal means this added AC signal does not disturb the DC characteristic of the applied potentials, okay? That is the definition of a small signal capacitance. In this case, the capacitance should be presented something like this, and then that is related to the space between those metal plates, right? So, step junction case. Q, or we know the charge per area. Area means the cross section of the junctions, right? And that is Q N D X D. And that is equal to Q N A X P. Okay? Actually, if you put the area to this this side of this equation, then XT times A is the volume. It's nothing but a volume of the semiconductor contains the charges, right? So here we can see immediately that the charge capacitance can be presented as the modulation of the depletion length with respect to the voltage, apply the voltages. So all you have to do is just get those numbers. Okay? Then how can you get that numbers? As we know, the xn is going to be, the total xd is actually the w that we just discussed, and minus xp, right? And then xd minus xp is nothing but nd over na xn, okay? Xn nd should be equal to the xp na for the charge neutrality, all right? So xn now is xd 1 plus nd over na. And then the xn can be expressed by the equation na and d phi I phi a. This equation, let's say na is 1 over na, and nd in this equation bar is nd. Okay, gamma that has been defined in the earlier. Okay. Oh, I'm sorry. It has to have a nominator which is 1 plus nd over na. So, the modulation of the depletion length with respect to the applied voltages now can be expressed as nd something like this. So the capacitance finally can be expressed all right, and if you have a C square, if you have a 1 over C square, then you can have the equations just like this. Okay? And if you plot this 1 over C square with respect to the application of the voltages, now you're going to have a straight line, and that intercept is related to the built-in potential, and the slope is related to the doping levels. Such a, let me see, this is related to the minus Z, where the Z is two gamma over Q, and NA plus ND. Okay. And then 1 over C squared now is going to be Z phi I minus VA. Okay. So this is important. We can obtain phi I and NA and D from the plot of 1 over C squared versus applied voltages in a junction. So you physically make a junctions, and then you measure the capacitance change with respect to applied voltages. Then you can determine how much dopant you have been put into your semiconductors to the junctions, and the built-in potentials. It is not easy to measure the built-in potentials in the junctions, but just to simply measure the capacitance of the junctions, then you can get the numbers correspond to the built-in potentials. That's how we measure the built-in potentials in the junctions. Okay, now let's look into the IV curve. Another important characteristic of the junctions, electrical properties of the junctions, that is current voltage characteristic in the junctions. Now, let's say in a p-type and n-type, here is a depletion region, and this is a neutral region, the p-type and n-type, and right at the edge, front of the junctions, let's say we define PP naught and we define NP naught, and PP naught means number of holes in P-type in equilibrium state. To be exact, we have to say to be in thermal equilibrium. Okay, we do not apply any voltages to the junctions, or we do not shine the semiconductors. In the dark, we just measure the number of holes, and that is going to be called P naught. Okay, naught means in equilibrium, and P small subscript here, the P means the P-type regions, and the big letter here, P, is the substance that we are talking about. Okay, so actually NP naught is the number of electrons in the P-type. So this is going to be the majority carrier. The holes in a P-type, okay? This is the electrons in a P-type, so that is a minority carrier. Minority carriers. Let me give you just a typical number to get some ideas when we talk about the minority and the majorities. Okay. Well, let's say if the silicon is doped with the borons, typical P-type dopants, like a 10 to the 20, what? 10 to the 19th. 19th per centimeter cube, okay? If then the number of holes here is about 10 to the 19th. All of this dopant is going to be ionized, we assume, okay? So that the number of holes in this P-type semiconductor is going to be the 10 to the 19th. And the minority carrier, the electrons in this P-type semiconductor, is going to be, how can it be calculated? Is Na over Ni squared, if it is in equilibrium. So Ni is about 10 to the 12 square of 10 to the 19th. So what is that? 1,000 per. Is that right? 24. Oh no. That's not right, right? 10 to the 5th per cube. Right? So the majority carrier, number of majority carrier in this P-type is 10 to the 19th, and minority carrier here is only 10 to the 5th. So when you say the majority and minority, we are saying tremendous difference. Okay, very much different numbers. Okay, so, and in the N-type, let's suppose we have a majority carrier is an N-type silicon like this, and the minority carrier P in N0 somewhere like this. Okay. Now it is if it is in equilibrium, somehow the number of number of holes here is going to be changed to this number across this junction somehow. Okay, and the number of electrons, which is this low, is going to change to this large number across the junctions. It has to. So that huge difference in the carriers forms the built-in potentials, band bending in this structure. So let's see the built-in potential. It's going to look like this, Na over Ni squared. And then that is Vt N naught over P N P naught. There is a difference in the electrons, number of electrons across the junctions. Okay, that is just related to the built-in potential. N naught is equal to Np naught e to the phi I over Vt. And the P naught is equal to Pn naught e to the phi I over Vt. Now what it says that the majority carrier can be expressed with the minority carriers. Okay, this is the majority carrier. Majority carrier in a p-type. Okay, this is the minority carrier in an n-type. But we are talking about the same species, the holes. Okay, so the number of holes is going to be enhanced in number by crossing this built-in potential in the exponential way. All right? That's what it says. Now, what happens if we do if we apply the potential VA? Okay, it's called the bias. We set the bias. What's going to happen? We are going to treat this in a situation low-level injection. Low-level injections. What does that mean? It means that after the application of the voltages, the majority carrier N naught is not going to change much. N. The N we omit the naught in the subscript because it is not in equilibrium anymore if you apply the voltages to the junctions. And the ferrome energies is not going to be defined because ferrome energy is the energy only can be defined in equilibrium. So if you suddenly apply the voltages to the junctions, then there is no ferrome energies anymore. We don't see any ferrome energies. We cannot define any ferrome energies. Anyhow, the low-level injection means with the application of the voltages to the junctions, the majority carriers is not going to change much from the equilibrium values. But we have a tremendous difference in the minority carriers. Okay? Let me give an example. if you have a 10 to the 19 p-type semiconductor silicon, and we just seen that in this case number of p naught is 10 to the 19th, of course, and electrons in this equilibrium p-type semiconductor is only 10 to the 5, something like this, okay? Now, if you dope this semiconductor a little bit more, then, here we go. If you doped this semiconductor like 10 to 21, something like this, okay? And then the number of holes is going to be 10 to the 21, and this is going to be 10 to 21, and this is going to be 10 to the third, so we just have a 1,000 number of electrons in this case, right? So let's just take an example, the heavily doped silicon, okay? And then it's 21, and we have 1,000 electrons, minority carriers in this p-type semiconductor. Now, if we shine the light and we create some of the generation rate, by the way, that G is, we shine the light and we create the electrons and holes at the same amount, like 10 to the 5th, for example. That is a very easy thing to do. 10 to the 5th creation of electrons and hole pair, 10 to the 5th, is not that we don't have to shine big lights. Right? That usually can be obtained. And then with this shining light, the PP, now majority carrier, is going to change in number like 10 to 21 plus 10 to the 5th, so that is 10 to 21. It is not changing much. But what about the MP in this case? Minority carriers. It originally has a 10 to the 3rd, and then now it has 10 to the 5. Because by shining a light, you are going to create the same number of electrons and holes, right? The electrons in the valence band is going to be across the band gap to sit in the conduction band with the light energies, photon energies. So we are going to have the same number of electrons and holes by shining the light. And then now the number of minority carrier is going to be 10 to the 5th. And this 10 to the 5th is a big difference with the 10 to the 3rd. So if you make a device to measure, to sense the changes of the minority carriers in a semiconductor, then that is going to be called photosensor, right? So the minority carrier change in minority carrier is tremendous. Same token, if you inject or if you apply the voltages, it's the same thing to shine the light. If you apply the voltages, the majority carrier is not going to change much. If the applied voltage is not big, not that big, okay? If the applied voltage is very big, so that it does really change the majority carrier numbers, then that's not going to be dealt with this normal equations. So that is not going to be treated in this lecture. And we're going to think about the low-level injection case only, and that low-level injection means the majority carrier is not going to change much, but minority carrier is going to change a whole lot. So that's the case where we are going to think. All right, we're going to discuss about this. We're going to continue the discussion of the p-n junctions characteristic, and then on the next Monday, we're going to discuss about the applications of the p-n junctions, and that is kind of a review. Okay. Have any questions? Okay, I'll see you on next week on Monday, and have a nice weekend.